If you stayed only 1 minute near a supermassive black hole, 700 years would pass on Earth. Is it confusing? Well, it should be, because time and space have very counterintuitive behaviors, such as time dilation and length contraction. These are explained by Einstein's theory of relativity. So, what is relativity? To begin with, let's briefly see what relativity is, then we will explain it with examples. The theory of relativity was introduced by Albert Einstein in the beginnings of 20th century. It actually consists of two separate theories, general and special relativity. According to special relativity, when an observer moves with relativistic speeds, that is speeds close to the speed of light, time dilates or slows down, and length contracts or shortens in the direction of motion. On the other hand, general theory of relativity is actually a theory of gravity. When an observer approaches a source of gravity, or when gravity increases for an observer, time dilates or slows down. Space gets stretched or curved, which is slightly different than length contraction in special relativity. By the way, an observer in relativity is actually a special person or a frame of reference from where objects and events are observed or measured. This is how relativistic time dilation, length contraction, and space curvature are defined. It's also postulated by Einstein that the speed of light is the same for all reference frames. According to these definitions, it's concluded that time and space are not absolute, but relative. In other words, time and space can be different for different observers. In addition, space and time are intertwined, forming the four-dimensional elastic fabric of space-time. This is shortly what the theory of relativity is about. Now, let's explain it with some fascinating examples. Until the 20th century, scientists like Newton thought that time was absolute and the same everywhere. However, this changed with Einstein. According to special relativity, time dilates or slows down for observers with relativistic speeds. Assume that you are in a spaceship which is moving with a speed of 0.8 times the speed of light relative to Earth, which is 8% of the speed of light. Also assume that you have a twin brother or sister who stays on Earth. You both were 20 years old when you left with the spaceship. If you live in that spaceship for 30 years, 50 years will pass on Earth. This means that you will be 50 years old while your twin on Earth will be 70 years old. This is known as twin paradox. Mind-blowing, isn't it? Well, not really, when compared to relative time near a supermassive black hole. According to general theory of relativity, gravity curves and distorts the fabric of space-time. As a result, time dilates and space gets stretched when you approach a source of gravity. The supermassive black hole in the center of our Milky Way galaxy, called a Sagittarius A star, has a mass of more than 4 million times that of the Sun, with a radius of 22 million kilometers. It has a tremendous gravity. When 1 minute passes at the edge of the event horizon of Sagittarius A star, 700 years pass on Earth. This difference happens as a result of gravitational time dilation. You may argue that these are just imaginary scenarios. Are there real events that support time dilation? Well, there is a lot of evidence. The simplest real examples are the GPS of your smartphone and the GPS devices in defense systems that work accurately thanks to the theory of relativity. Due to high orbital speeds and slightly weaker gravity than on the surface of the Earth, time flows slightly differently for the GPS satellites. These are tiny differences, but can introduce significant errors in geographical positioning, up to several kilometers. Therefore, the GPS systems consider these subtle differences in time to make accurate positioning calculations. Another shocking news that the theory of relativity introduced about the universe was that the space is also not absolute but relative. In other words, distance between two fixed points in space can be different for different observers. Let's see what it means with an intriguing example. The closest star to Earth is Proxima Centauri, which is 4.243 light-years away. For simplicity of calculations, let's assume it as 4 light-years. Suppose that you want to go to this star in a spaceship which travels with a speed of 0.8 times the speed of light. How much would it take for you to reach the Proxima Centauri with this spaceship? According to classical or Newtonian physics, it will take you 5 years to reach Proxima Centauri with this spaceship. However, according to special relativity, since you are traveling with a relativistic speed, the distance to Proxima Centauri will be contracted. For the speed of 0.8 times the speed of light, the length will be contracted to 60%. So, according to you in the spaceship, the distance to Proxima Centauri will be contracted to 2.4 light years. Therefore, since you are traveling with a speed of 0.8 times the speed of light and the distance to the Proxima Centauri is only 2.4 light years to you, then you will reach there in 3 years. Mind-bending, isn't it? Think of it this way. Since the distance is considered to be 4 light years, then light will reach there in 4 years according to us on Earth. However, with the spaceship moving with only 80% of the speed of light, you can reach there in 3 years. How can this happen? Doesn't it sound like you reach there before light? Well, not exactly. Since the distance is 2.4 light years to you, then according to you, light reached Proxima Centauri in 2.4 years. Time dilation and length contraction are actually related to each other. Consider the above example. You reach Proxima Centauri in 3 years according to your clocks. However, our clocks measure this time as 5 years. According to us on Earth, you traveled for 5 years. This is because time is dilated in your reference frame as observed from Earth. So, our distances get shorter for you and your time is dilated according to us. It is a compelling example, isn't it? But again, it is a made-up scenario. Is there any real example? Yes, there is. The muons are elementary particles which are generated in the upper layers of our atmosphere. They are very unstable elementary particles with extremely short lifetime, but they move with near the speed of light. From Earth's reference frame, these muons can travel a maximum distance of 456 meters throughout their entire lifetime. So, classically, there is no way that these muons reach the surface of the Earth. However, the muons do reach the surface of the Earth. This is because of relativistic effects of muons' relativistic speed. Due to time dilation in a muon's reference frame as observed from Earth, they have longer lifetime and can reach the surface of the Earth in that period of time. On the other hand, the distance to the surface of the Earth contracts to muons due to their relativistic speeds, and they travel less than 456 meters before they can reach the Earth's surface. This is why time and space are intertwined, forming the four-dimensional space-time. Considering all the materials that we discussed until here, what do you think about time? Is time real or an illusion? Well, that's a story for another video. Keep tuned. Please subscribe to our channel to support our work and help us bring more interesting videos. Like and share the video with your friends if you found it interesting. Thanks for watching. Bye.